Okay, so we are still talking a little bit more about hydrolysis of salts. Okay, the lecture 12 slides. So this that I put here on the board is a little recap summary of the different salt that we talked about yesterday. When is a salt neutral, acidic, basic, right? So I'm going to leave this up on the board, so I put it on this side while we work through some examples today, so you can just keep I can keep coming back to this. I wanted to add 2 more statements, okay? For acidic salts, I do want you to be aware that salts that contain, in addition to these conjugate acids of weak bases, okay? A salt is acidic if it contains, let's try it. A salt is acidic if it contains metal cations. Except which metal cations? These metal cations. Group 1, lithium, sodium, potassium, blah, blah, blah. Those are inert. I've told you, they are not acid or bases. They're neutral. Calcium, strontium, barium, also inert. Not acid, definitely not base, but not acid. But other metal cations, like a lot of the transition metals, iron, copper salts, zinc salts. Those compounds are often also acidic. The chemistry of their hydrolysis, so how do those metal ions undergo water reactions, is not something we can talk about right now. I want us to be able to talk about it, but as y'all know, we're running short on time. So I want you to know that if you see metal salts, they're acidic unless it's one of these cations, right? Okay. And then the other thing that I wanted to add is, what if you have a situation where your salt has both the kinds of ions that can undergo hydrolysis? What if you have a situation where they both are going to react with water? You don't have anything that's inert. How do you know whether the solution, how do you predict? How can you predict? It's pretty easy. So I want to go ahead and do an example. Let's try to just do an example so you can see how we predict, right? Because you only have 3 choices, right? The salt is either neutral, basic, or acidic. These are very common combinations. So let's look at an example, and then we'll see one where you have to choose which one it's going to be. Let's do that. So I'm looking on our brand new in class. I'm looking at number 8. And then we're going to come back and do those math examples that I told you we would do yesterday. But let's look at more just comparison, okay? So number 8, I gave you guys a table of various different Ka values and Kb values. We'll go refer to some of those for some of this, okay? So look at the first salt formula that I listed, KBr. KBr. What do you observe when you look at the formula for KBr? K, your cation, is what kind of cation? Why is it inert? Because Potassium is a group 1A. Okay, so this is inert. What about the bromide ion? What about Br minus? What about Br minus? Well, Br minus is the conjugate base of what acid? It's the conjugate base of HBr, hydrobromic acid, which we should all recognize as being a strong acid. And therefore, this conjugate base, this bromide ion, is also inert because it's the conjugate of a strong acid. That means that the salt, potassium bromide, is what kind of salt? It is indeed neutral. Okay, let's look at the next one. Did you see my thought process going through that right there? I look at each cation, anion, and try to figure out what is it, right? Okay. What is the next compound I have? Sodium something? Sodium what? What's that called? Sodium hydrogen carbonate, or you could call it sodium bicarbonate, which is what I say. Okay, sodium hydrogen carbonate. What are the two ions here? You've got a sodium, which is what kind of cation? Absolutely, it is inert. Group 1A, inert. Okay, what about my anion? This is a polyatomic ion. Okay, this is the HCO3 minus polyatomic anion. What is it the conjugate base of? It is the conjugate base of H2CO3. So we recognize that this is the conjugate base of a weak acid. And what does that mean? This means that when you dissolve this in water, what will you see occur? The sodium won't do anything, but this basic anion will undergo base hydrolysis. And so our solution is going to be basic. First one was neutral. This salt solution, the salt sodium bicarbonate, is a basic salt. You want to prove that? I have a test too. Okay, so here's some sodium bicarbonate dissolved in water. Okay. If it's basic, if it's above 7, I ought to see that in this indicator that I'm using. It should be the exact value depends on what the pH is, but it should be maybe dark green or even bluish, blue-green. Let's see if this one works. Right? Let's see if this one works. Ooh. It's actually pretty basic. Actually, this, see that? Kind of purple. You see it, Kate? Yeah. Okay. Okay. Base. It's a basic salt. Basic. What about the next one? Okay, I got another sodium. Guys, this little ion right here, when we start talking about buffers tomorrow, this ion, the bicarbonate, and this ion become real important. I would absolutely recognize this is the polyatomic ion called what? You want to name that? This is called just hydrogen phosphate. It has a -2 charge. What is it the conjugate of? This is my anion. This is my conjugate base of what? H2, PO4 -1. And then I would keep going for that compound. I would keep going. But I'm just looking at one at a time, right? Dihydrogen phosphate. Guys, is this dihydrogen phosphate a strong acid? It is not. It is a weak acid. So sodium is, of course, inert. So if I have a salt, if I have an ionic compound that has the conjugate base of a weak acid, that salt is therefore what? Basic. Yep. Okay, and so now here's the example that I wanted to do with you guys. What if your salt contains both basic and acidic ions? How can you predict? Of course, guys, could you always actually go get a pH meter and measure the pH of anything and know if it's acidic or basic? For sure. And that's the lab that I hope for us to do either tomorrow or Monday, and I'm not quite sure. I'm kind of thinking about Monday because it's a low-key lab, and I think I want to do the high-key lab tomorrow and do the low-key lab on Monday, that it'll be more like a review for the test the next day. That's kind of what I'm thinking. But anyways, I digress. How do you just predict? And you just predict. So D, I have what compound? Ammonium something. Very good, Joseph. Ammonium cyanide. Sounds very poisonous. And it would be. Yeah, it would be. We don't want to drink this salt solution, guys. Okay? No, 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 no. What are the two ions that I have? What's my cat ion? What's the first ion listed? Okay, I got ammonium. Let's talk about what is ammonium. Ammonium is the not inert. It is absolutely not inert. It is not inert. Ammonium is NH4 plus. That means it is the conjugate acid of what base? Very good. That means ammonium. Sorry, Veronica, do you want me to move it somewhere? Can I move this way a little bit? Maybe that helps. Okay. It's always you on this side, Veronica. That means this ion is what we would call a what? Acidic. It's an acidic ion. It's the conjugate acid of a weak base. It's acidic. But here, my anion is not inert. How do I know it's not inert? Let's think about it. This is my anion. It's negatively charged. What is it the conjugate base of? Hydrocyanic acid. It is the conjugate base of a weak acid, just like these two examples we saw a minute ago. Let me put some words here. The NH4 plus is the conjugate acid of a weak base, right? That means it will do hydrolysis. This The cyanide ion is the conjugate base of a what? A weak acid. It's not a strong acid, it's a weak acid. That means the cyanide ion will also undergo hydrolysis. Which one wins is how I think about it. Which one takes over the solution? We got to actually look at K values now. It's not necessarily going to be the acidic one. The only way, you guys, the only way you can tell in this situation is to compare the K values. That's the only way to know. Okay. So I want to compare K, what letter for NH4+? This is an acid. I'm looking for Ka. This is going to act as an acid, right? Therefore, it has a Ka value. I want the Ka value for NH4+. Versus what? Kb base for this ion. Okay, go look in your table. I got to give you some data to make this comparison. Go look in your table. What did I give you in the table? I gave you NH3 and I gave you HCN. I did not give you these conjugate values. I gave you the actual acid and base values. How do you turn a Kb, for example, of NH3 into the Ka value of its conjugate? You solve for the Ka by doing Kw divided by the given Kb for that weak base. Yes. Yes. That's how you solve for Ka. It's how you solve for any conjugate K value, right? Anytime you have a K of a conjugate, you can solve for it if you have the other K value. So if I need the cyanide ion K value, if I need Kb for the cyanide ion, what value am I looking for in that table? I'm looking for the Ka of HCN, right? Okay. When I solve for the Ka for NH4+, I get 5.6 times 10 to the negative 10th, I think. Does that sound right to anybody else? You checked it?
It's just rounding out. It's just still.
Okay. So that means, and then now the Kb for the cyanide ion. 2 times 10 to the negative 5th. Is that right? Ooh, I'm good at remembering those numbers today, y'all. Actually, the ammonium one I do know right off the bat. But I only know this one because I was working the problem earlier this morning. And I just remembered what it was. But I do know that one off the top of my head.
Wait, so the lowest one is no?
The highest one wins.
So
The strongest K value is bigger than negative 10, right? Mixed up in your head. I know it's real easy to do. With negative exponents, it can be easy to mix that up. I'm telling you guys, okay, there we go. Yes, that's me in my notes too. No. I'm telling you guys that when you're comparing K values, the bigger K value is the one that wins. And so that means that this salt, ammonium cyanide, is what in water? Basic salt. I didn't mean for all of those to be basic, but that's what they ended up being. Okay. If you want to practice this exact thought process again, you can look at the next one, number 9. You could even look at number 10. It's also kind of this same thought process. And those answers are, as always, in the slides. That's what we're fixing to do. Numbers now. We talked about how to just look at, for the most part, not so much doing stuff with numbers. We did just then, but mostly we've just been looking at, well, what's this and what's this, and I can predict this. But what if I actually ask you to calculate, tell me the pH of this salt solution? I want the actual pH number, not just acidic, basic, neutral. I want the number. That involves ice table. That is solving for X, solving for hydronium concentration, solving for hydroxide, turning that into the pH value. Okay, so let's practice that. Here are the 4 examples that deal with this. I'm only going to work 2 today. Here's the 4. Numbers 4, 5, 6, and 7. Okay. 4, 5, 6, and 7 are all pretty much what's the pH of this salt solution. Okay. What's the pH of this salt solution? So I want to look at 4, probably 4 and 7. Okay, so looking at number 4. 4 is describing this compound that you are not used to seeing, I know, okay? It's a compound called aniline. Okay. Aniline is used in manufacturing, okay? So here I'm telling you, it is isolated as anilinium chloride, and then here's this formula, okay? And I tell you, this compound, this anilinium chloride, is a what? It's a salt. Here's our salt. And in fact, I even went ahead and wrote the hydrolysis equation for you. But if I didn't give you this hydrolysis equation already, I expect you to be able to look at a formula, even though it's a compound that we haven't seen before. Because there's something in that formula that you ought to recognize. See, what is this? C6H5 NH3 plus, right? And then there's my chlorine. Guys, this is a salt, which means there is a cation and an anion. Oh yeah, I'm just talking about the salt, right? Salt has a cation and an anion, right? Right? What's that first thing listed always? It's my cation. What is this cation? This is what you think to yourself. This cation is the conjugate what of a weak what? This cation listed first is the conjugate what of a weak what? NH3 plus. NH3 plus. NH3 plus with all this other stuff attached. So this is the conjugate. Yes, you guys. You remember when I told you that any kind of compound that has nitrogens in it, normally they're bases. I add a H to it, and now it's the conjugate acid. Now it's plus, right? That's the conjugate acid of a weak base. What is this ion? Ooh, of a weak acid? Chloride, Cl minus, is the conjugate base of a strong acid. What's the strong acid it's the conjugate of? HCl. Therefore, the chloride ion is what kind of ion? Inert. Chloride ion is inert. That, Loretta, is why the chloride ion is not in that hydrolysis equation, right? Because the chloride ion doesn't do anymore. Does, okay? The what ion is going to undergo hydrolysis? This one right here. The one that's a conjugate of a weak substance will do hydrolysis. So I gave you, like I said, I gave you the hydrolysis reaction, but even if I didn't, you guys need to be able to write. And what kind of hydrolysis will this do? An acidic hydrolysis reaction. How do we know it's going to do an acidic hydrolysis? Because it's a conjugate acid. That's how we know. Also, in case you guys haven't realized, the cation is always the acidic one. The cation is always the acidic one. The anion is always the basic one. You guys need to get used to seeing these conjugate acids written in just this generic way. That's what I'm going to write right now on the board, okay? What am I using this BH plus to represent? This thing. Okay, that's that. If it's an acidic hydrolysis, what is it making? Just the base and then hydronium. That's why it's acidic. It makes hydronium. That's why it's acidic. ICE. What is it I want at the end of the day in this problem? What's the pH? To know pH means I need to solve for hydronium at equilibrium. Okay. What was I told that I can use to fill in this ice table? 0.233 molar salt. So that means the concentration of my cation is also 0.233. Yes. Why? It's a 1-to-1 ratio. The salt dissolves completely. Okay. The salt itself dissolves completely. It's the cation that's now doing the weird equilibrium thing. If it was not 1-to-1, I don't think you're going to actually ever come across that in any of these problems. But yes, if it was not 1-to-1, let's say it was 2 of these, you would multiply your initial by 2, right? It's ratio, mole ratio. But I think you're not going to come across that. Water never fills in anything, right? Sorry. Initially, I don't have any of the base, the weak base, and I don't have any hydronium. This conjugate acid cation is going to decrease. These two are going to increase. And so at equilibrium, it will be that much, it will be that much, and there will be that much, right? Good, very good. Now here's the only, I was gonna say here's the only tricky thing, but maybe y'all thought that was tricky, so I don't know. Let's see. Here's what you need to recognize. What K value did I give you in the problem? I gave you a KB, a base value of what? Aniline is how I say it, but be sure. Okay. I gave you the K value for the base form. It's a base. That is not the K value I need to solve this equation, though, is it? What do I need to solve this equation? I need Ka, because this is an S. We got to do that thing again. Okay, here we go. So, given Kb for the aniline, I need Ka for the actual cation that I have. I need Ka for my acidic cation. How do I solve that? What we did a minute ago. Water's constant divided by the given one. Water divided by this given one in the problem. What is water's constant? 1 times 10 to the negative 14. Okay, so I'm just going to write the, let's see, what's the number? 2.3 times 10 to the negative 5. Okay, so here now is my Ka value. Just like previous problems where I give you the Ka value, you just had to calculate it for yourself first. I know, it's rude. It's rude. Okay, so now you got your K values, you got your ice table. How would you solve for X? Yeah. Yeah, how would you solve for X? You would do Ka equals, yes. You can, and we're gonna absolutely make that assumption and save ourselves from doing a quadratic. Okay, I would do this, and then I would say, well, that means I'm doing x squared on the top. And I've got my little subtraction equation on the bottom. And that equals that. And like Joseph said, I am absolutely, guys, going to make the, let's assume X is small. Why can I make that assumption? Who wants to answer this for me? Okay, X is small. Wow, I haven't been to a mall and I don't know how long. Okay. Because the K value is very small, 10 to the negative 5th. Anything smaller than 10 to the negative 4th, you're probably okay to make this assumption. Compared to my initial given value, which is 10 to the negative 1st, if I put it in scientific notation, that's a huge difference. X is going to be very small. I can ignore it here. I can ignore it here. So solve for x. Let's assume x is small, and so this is really just using the number 0.233, right? That's what we're assuming. Here we go. Ooh, okay.
It's 5% or less, that's valid, right?
Yeah, when you check the 5% rule, if it's less than 5%, 5% or less, then that was a fine assumption to make. If it's greater than 5%, you got to solve x as a quadratic equation. Okay, so I got, in the interest of time, I'm not going to write through the steps. Just here's what I got for x. No, 3. -3. Okay, and if I check my 5% rule, which you should do, you should check. You should check it every time. When I check that 5% rule, I'm basically doing percent ionization, right? Isn't that what we saw yesterday? Okay, I'm taking my x and I'm dividing by whatever initial concentration I had and times 100. And this check comes out to be like 0.99%. That is absolutely a valid assumption that we made. Yes. We can, that means we can safely say that this x is the what? The concentration of, and I care about the hydronium ion concentration because I asked, what is the pH? And for that, I need hydronium. And I got 2 sig figs, 2 places after the decimal point. That means a value of 2, pH of 2.64 is what this solution has. That means this is a what kind of salt? The pH is less than 7. It's acidic. We could have just predicted that. And we did predict that. But this is the actual value of the pH if I measured it with a pH probe. Okay, look at 7. On number 7? Oh, acidic, because because the pH is less than 7, and we had this acidic cation in the formula. We should know, yeah, that's an acidic solution. Yes. Okay, we'll look at number 7. What's the pH of a solution? And I give you the molarity of this compound. You'll name that compound. Sodium cyanide. It is not very good. No cyanide is ever good. Okay. Can you guys just predict for me? Is this going to be acidic, basic, or neutral? I'm making a face. I'm making that face. Number whatever we looked at, whatever. Whatever it was. That's what we got to remember. What's the first thing listed? The cation? Sodium? Okay. Second thing listed, Cn minus. Is a what? It's the conjugate what of a what? conjugate base of HCN, weak acid. That means the solution is going to be what? Basic. This is going to do a what? Base hydrolysis. The sodium is going to do what? Not a damn thing, right? Not a damn thing. This is going to do the thing. And what it's going to do is base hydrolysis. So, write that. I did not give you the equation here. I'm not going to give you the equation on a test. Is that true? At least one I'm not. I love for you to use B and A as much as you want to. This one, I am actually going to write the C in because it's just 2 letters. But like that previous one, instead of writing all those letters, you can just use BH plus B. You can do that. You can do that here too. I'm just not going to, unless y'all want me to. It's whatever I want. Damn straight, it's whatever I want. I'm a teacher, damn it. Okay, when this guy interacts with water, I'll tell you this, if I was going to put a symbol here, this is the symbol I would use. I'm talking about this is the conjugate of a weak acid. The symbol I would write would be A minus, because this I would write as HA. That's how I would do that. HCN, because this goes to this, right? And then that leaves, which is why this is a base. That's why this is a base. Yep, that's why this is a base. Maybe, let's see. But that's the Ka. What do I need? Okay. So that is maybe even the very, after you write the equation, that is maybe even the very next thing you guys should do is be like, I need Kb of the cyanide ion. That's what I need. I was given Ka of the conjugate. So let me do my little math. Like we saw before, right? Cyanide K, the Kb of cyanide doesn't change. It is what it is. At that temperature, but we're not playing with temperature in this class, thank God. So everything is room at 25 degrees C. Everything is 25 degrees C. So easy. Oh, if you were going to do advanced equilibrium in an advanced physics or chemistry class, then you can play with temperature. But yeah. What do we have initially? 0.083. Guys, these start to be very repetitive in how they fill in. Yes? That's a good thing for us. Practice makes perfect. So my Kb expression is these two over this thing. So I got x squared over 0.083 minus x. And that equals this K value we just solved for. That equals this value, not the value given in the problem. I know, because this is a salt and it's got to be difficult. So now, Loretta, look at these numbers and say, can we assume? I still think we can absolutely assume. Caitlin, why can we assume? This is -5. And then 2. That would be times 10 to -2. Those are far enough apart. We can absolutely make this assumption for sure. Yes. So that is our assumption, which makes this way easy to solve for. Assume x is small. It should be like 1 point. Yeah, it's pretty small. After you've solved for x and you come back and check. Okay. So solve for X. Very small. I got the actual value of X to be 0.0013, or if you put it in scientific, 1.3 times 10 negative third. And we're saying that is our equilibrium hydroxide concentration, right? If I check my 5% rule, I got 1.6%, but that's because I used this rounded number, but that's if you got 1.4%, guys, we're below 5. That's the whole point. Okay. And so I know you guys are like, I've already done this and this and this, and I'm still not done with this problem. No, you're not. Because what is the problem asking? What's the pH? So what we will do is with this kind of base hydrolysis, right? What we do is we first find POH, negative log of this number. I got 2.89, but it's, yep, okay. And you guys are going to be like, there's my answer. No, because that's the POH value. What is pH? Yes, you guys. pH 14 minus that number. 11.11. Basic, like we predicted it was going to be? Yes. Very basic. Good job, you guys. Okay, we got one more topic to talk about, and then we'll be done for the day. Okay. No, y'all can do it. Y'all are good. Y'all are good. Y'all are just fine. But food, I know. Y'all fine. We got to do this one topic, and then that way tomorrow we just have 2 sections left. We'll see. Buffers and titrations. Okay. Same set. I'm going backwards in number to that section 4.5. So we finished 4.4. We finished talking about salts. Okay. What I want to look at real quick is, oh, we'll Boromir again, but hang on. Hang on. But that's the thing is y'all are all passing right now. Y'all are passing very well right now. So I don't know why all y'all get all freaked out. Come on, y'all are doing great. Y'all are doing great. Y'all are fine. Y'all are doing just fine. Okay. Polyprotic acids. Section 14.5 called polyprotic. I am not going to do a deep dive into this topic because we just don't have time. And, you know, we got other important stuff to talk about. So we're just going to lightly hit this section. Okay. Very light tap tap. Okay. Real light. Y'all are like, Ms. Poe, when you say light, that doesn't mean the same thing as when I say light. It doesn't mean the same thing as Poe. Okay. Here, I'm going to put this up here. These are the 4 statements I'm fixing to make, and then we're going to look at some examples. But basically, if I say the word monoprotic, mono exactly means 1. So some acids are monoprotic. So, for example, monoprotic acid means there's only one H plus in that acid compound that it can give away, right? Because acids give away, right? If you're trying to be fancy, you might say it only has one ionizable H+, okay? Just has one. What are some examples of monoprotic acids that we've been seeing a lot? Oh, something like the most HCl. Okay. HCl has how many hydrogens, protons that it can give away? Yeah. If I'm thinking about the molecule itself, like if I draw a little Lewis structure, yeah, that's the one it can give away. That's it. Not all of them are monoprotic. A lot of them are monoprotic. There's a couple that are this other word, right? Okay. So what about this acid? Okay. HNO2. Maybe the name of that one? This is nitrous acid because it's the NO2 ion. NO3 would be nitric acid, but either way, this would be classified as a what kind of acid? Monoprotic. And I'm going to go ahead and put another one up here, and I want to show you something real quick. What would be this acid? My favorite, right? That's Ms. Poe's favorite acid, acetic acid. I want to show you guys with these two monoprotic acids. We could also call these two acids what kind of acids? The fact that they have oxygen in them means something. Oxyacids. Binary acids just have H and one other element. Oxyacids have H and another element and oxygen. But in either of these, when we're talking about monoprotic, if we look at the structures of these two examples, okay, any monoprotic oxyacid, I thought y'all might be interested to know, right? Where is that H attached to? And I want to do NO2 or NO3. It doesn't really matter if I do NO2 or NO3, either one. Let's, I guess I'll look at NO2. So, very good, Joseph. Can you say that again? Probably because it's more electronegative. Joseph has his thinking cap on today. Very good. Over here. Okay, over here. Sometimes I've talked to you, I think I've talked to you guys. You guys might see acetic acid in some of our examples written this way. You ever seen it written that way? Okay. I don't care for this way until we get to like this part of a chemistry class, because I like this way because you can see here that it's this ion and then this ion. But when we think about it put together this way, what I'm writing is more of the order that these are connected, that these are bonded in. I'm writing the order they're bonded in. So this particular hydrogen is not actually bonded to a carbon. These hydrogens are bonded to a carbon. And then that carbon is bonded to another carbon. And then that carbon is bonded to an oxygen. And at this point, well, actually, we're supposed to study this in Gen Chem 1, but if y'all don't know why I'm drawing dots somewhere and lines somewhere, I'm sorry. What else to tell you? I'm sorry you don't know that. When I talk about this is a monoprotic acid, it only has one hydrogen it will give away. Which hydrogen is acetic acid willing to give away? It's the one that's attached to the oxygen is the one it's willing to give away. Okay. Acetic acid will never give away those hydrogens, ever. They're too strongly bonded. And as Joseph said, This is a very polar bond because oxygen is very electronegative, and we talked about that yesterday. The more electronegative this is, the weaker this bond is, the easier it is to give that hydrogen away. Okay, monoprotic, only one. Polyprotic, more than one.
So do we need to know which one is giving away?
No, that's really more just for your personal information. Like I would never want you to look at this formula and think, oh, this acid can give away 4 hydrogens. No, it cannot. Okay, cannot. If you see formulas written this way, which is the hydrogen that is ionizable? The one attached to the oxygen. Personal knowledge. 5 bonus points. Okay, so if we have polyprotic acids, that means we have more than one H we can give away. Chill, be fine. It's an example of a polyprotic acid.
H2 something?
Sure. So what we see with polyprotic acids is that the acid itself is not amphoteric. The acid is just an acid, but its conjugate ends up being an amphoteric species. That is what we see. So H2S, right? Is that a polyprotic acid? For sure. It's got 2 hydrogens it can give away. Here's what I need you to know about polyprotic acids. They only give away how many at a time? 1 at a time. So I can end up with the conjugate, which is HS minus, right? Right. So now I only have 1 hydrogen there. But then this could conceivably do what? Give away another one, and I end up with S2 minus, right? But it only does it 1 step at a time. What about something like, what was the other thing? A real important one, H2CO4. H2CO3. Huh? I don't have to. I don't have to. Absolutely. I don't have to erase it. I don't have to erase it. I'm glad you stopped me. So I was about to. It's fine.
I mean, I know it's just S, but S, but it's not. I know, but it makes me get some. It's alone. Just know that it's alone.
Okay. What about this? H2CO3. Monoprotic or polyprotic? In fact, we might even just say diprotic sometimes if it is just 2. But yeah, polyprotic. What does it turn into? HCO3 and then yes, okay. And if I was looking at the structure of it, I would observe that those hydrogens are attached to not the C. That was the whole point, right? They're attached to the oxygen. Okay. Okay, so each one of those is 1 proton at a time. Can you have even more than that? Sure. We got some triprotic acids like the phosphoric acid, right? How many ionizations does it have? It can go 1, 2. I hate when I get to the middle of the board like this. What would be the charge here? -2. That's -1, that's -2. And then finally, what's the last thing that I could? PO4 -3, the phosphate ion. Yeah, there's 1, 2, 3 steps. Each step has its own acid hydrolysis and its own K value for that hydrolysis. Acid hydrolysis number 1. What is this? Acid hydrolysis number 2. What would be title its K value? We would say Ka, Ka2, okay? Here, Ka1, Ka2, Ka3. Yeah, okay, step by step. Each time we do this with polyprotic acids, the K values get smaller at each step. Okay. Each step they get smaller. I think pretty much yes. If you were talking about base hydrolysis, you would have this accepting a hydrogen, and there would be a Kb for that. And there would be a Kb2 for that. Yes. So it would go the exact same way. I have made the decision in this class. We pretty much are just going to look at acid down. Yeah. Okay. Because we only have so much time. All right. What I want to say is the main polyprotic questions that I ask are typically concept, right? How many hydrolysis steps would it have? Is this polyprotic or is it monoprotic? Okay. But I did put on the homework 1, I think, math 1. Let me see if that's really true. Hang on. The homework that's out now, that's not due till Monday. Yeah, I put 1 math 1. 1 math 1. It's number 13. Number 13 on this new homework set is a math 1. So I'm going to tell you guys, if you want to know how to solve that, come look at this example. Not this one. Yeah, that was just 1. That's number 2. Okay, this what I'm sharing here right now is number 2 on our in class. Okay. You can certainly, I mean, this is not unhelpful as well. I mean, you can certainly go through that. But really, the one that's more in line with what that homework question is asking would be example 3. Which, I don't have the solution on there. Okay, I'll add the solution on there. My bad, dog. Okay. I'm so sorry, you guys. I don't know what happened. Okay. I will put the solution for, you might, because it's actually not nearly as hard as you think. I mean, it's basically what we've been doing. No, see, that's what you're going to realize when you look through it. It's not really actually times 3, because the numbers get so small that we start to assume and ignore them. So, okay, the numbers get so small that we start to be able to ignore things. Okay, so it's really not that bad, but okay. I know, right? Okay, this one, either number 2 or number 3 on these in-class examples would tell you how to do this math. Okay, so I'm going to tell you guys to look at those. Everybody heard me? Everybody got? And I will make sure this solution gets put into these slides. Yes. Okay. Please pick up on your way out numbers 2 and 3. This worksheet. Ooh, what? No. hang on. This is, I have them right here in my hand. So this is your lab worksheet to work on over the weekend, right? About acids and bases. So I'm gonna go ahead and hand these out to you guys. And there are a few questions that you could not do today. Thank you. But the vast, like at the end of the packet, because we got to talk about it tomorrow. You want to challenge yourself, go right ahead. Okay. So this is y'all gonna be working on this over the weekend. I would go ahead and maybe just take a look at some of it tonight, but the last page of questions, absolutely wait till after we have class tomorrow. Okay. That's